many, many jumps. As long as it's a more general notion.
So we don't have to have countably that this comprehensive
Right. Yeah, the basic thing here is now we're into the second video now, but that's okay. But this will be a short one. Yeah, I think so. Properly speaking, the Riemann integral is geared up for continuous functions. If you look at the proofs of the major theorems of Riemann integration, they're all the continuity of the functions you're integrating. It's all baked into the theorems. Like we use the intermediate value theorem to prove things. We use the extreme value theorem to set up things like the fundamental theorem of calculus, right? The continuity is so much of what we do. So I don't know, this doesn't require continuity of the function in order to set up the integral. So, I mean, I don't know. So how do you break the Riemann integral is really the question I'm kind of asking. And I'm sure we'll come to more examples. I think you'll have examples of that as we go on and develop this Lebesgue integral more deeply. Let's see, flash forward ahead. Next, we're in section 2.3, so next time we'll learn about if you had two different representations by a function in terms of a different sequence. If you had, a function represented by two sequences of step functions, well, guess what? They give you the integral that they define, it's the same. So like you could have different sequences of step functions. This would still be well defined. This is independent of your choice of sequence of step functions to represent your function. And
I had that question earlier on.
Right. And then he'll define the space of all such functions as L1R, and we'll prove various theorems about that. Then after that, he talks about the absolute value of an integrable function. He proves theorems about that. And then he talks about series of integrable functions, and we look at how to do series of integrable functions. Then he gives a norm in section 2. In section 6, we get the norm of the function, and talk about convergence in the norm and all that. And then finally in section 2.7, we get to convergence almost everywhere. And I think that's where these ideas really come to a little bit more life. There in definition on page 56 in definition 2.7.6, he says we have a sequence of functions f1, f2, defined on R, converges to f almost everywhere, denoted by fn goes to f, ae, i.e., meaning that fn of x goes to f of x for every x except the null set. So that concept there starts to sort of scratch the itch we're starting to feel today. And then what's past that? And then finally, section 2.8, fundamental convergence theorems. Something about subsequences here. Eventually, we should get like monotone convergence theorem, Lebesgue dominated convergence theorem. That's a big one. And then Fatau's lemma, which is sort of the reminiscent of the Weierstrass test, but not quite that. Then we talk about locally integrable functions, and then what happens? Eventually, we should get back to like the section 10, the Lebesgue integral and the Riemann integral. So finally, in section 10, we will properly discuss the connection between the Lebesgue integral and the integral that you saw in calculus, perhaps. And we'll get things like the fundamental theorem of calculus is in that section, and change of variables, and then I think finally section 11 he talks about measurable, like what's a measurable set, and things like that. And that's, I think, well, there's more of the chapter, but that's all I've got a copy of. Oh, and then he turns to complex. Then I think at the end of the chapter he turns to the complex value, functions of complex variable, and then eventually functions of Rn. So yeah. But anyway, there's where we're going. I will try to not belabor any kind of technical proofs in this chapter too much, because I find that it's easy to spend a lot of time on proving something in this material and then kind of not get a lot out of it. So I'm going to try to keep a good clip through here. So Anyway, I'm going to hit the video over here, Audric.